Maybe I'll just follow that. It's probably going to be easier. What is a vector?
Is that a question, or are you just going to write the answer?
I'm going to write the answer.
Okay.
What do you think it is?
Direction and magnitude.
Well, it's not direction and magnitude. It's a something with direction and magnitude.
Something with.
So pretty close. A quantity with, or maybe that has magnitude and direction. Okay, what's magnitude? That's a funny word.
A scale.
A scale?
Okay.
I got the right idea, but we need better words.
A measurement that measures how big, strong something is.
Beautiful. Big is a good word, right? Magnitude tells me the size. Think magnitude 6 on the Richter scale for an earthquake. It tells me how big this thing is. So it's got a size, it's got a bigness, a magnitude, and it's got a direction. Most of the stuff you've worked with so far, most of the objects you've worked with in maths have just had magnitude. If I take a measurement of something and say 10 kilograms, it's 10 kilograms. Up or down, I don't care, it's just 10 kilograms. But if you do physics, you've just done momentum. Have you done momentum?
Yeah, we just did.
Momentum is a vector because it also has a direction. Distance is a scalar. Scalar is the opposite of a vector. Distance is just how far. But displacement or force, these things also have a direction. So, understand the difference between a scalar and a vector, so distance and displacement. So let me go scalar, vector. And I can go distance and displacement. Think about what this means. The distance from me to the, that's a bad example. If I'm going to walk to the television over there, the distance I walk is 1, 2, 3, 4, 5, 6, 7, 8 metres. The distance I moved was 8 metres. But my displacement is actually more like 6 metres.
Square root of 32.
Whatever it is, right? It's more like 6 metres.
Northeast.
Well, in this case it's northwest, but yes. That's north.
Yeah, I was just assuming.
Yeah. So displacement tells me the distance and the direction from the start to the finish. That's a vector. The distance tells me the total travel distance. Make sense? Same goes for, what's the next one on their list? Speed and velocity. Speed, I'm walking at 6 kilometres an hour. But if I went in a sort of a zigzaggy thing, my displacement might actually be less in magnitude, so my velocity would be a smaller number with a direction.
If you wake up in your bed and go to sleep in the same bed, your average velocity for the day is 0.
0, correct. Because your displacement for the day is 0, correct.
Yeah.
Correct. And then they've got magnitude of force and force, same idea. Right? What are some other things you might be able to put under scalars? I'll put force here because it is a vector. I've talked about one already. Can you think of some other scalars?
No.
Brian, Ben?
Is weight?
Well, okay. Weight is kind of a combination of mass and force. Force technically has direction. Weight is always downwards.
Time.
Sorry? Time, good.
Can time have a direction?
No.
Can it not?
Time doesn't have a vector. Sorry?
But can you not be back in time and forward in time?
That's plus and minus. That's not the same as direction. Doesn't make sense to talk about time, time leftwards or time up and then right. That doesn't make any sense.
But you can say backwards or forwards.
Along a single line, one single dimension, so no direction.
Okay.
It's a positive and negative. Electric charge, same idea, right? What about some vectors? Are there any other good vectors you can think of?
No.
What's another vector you might have come across? Oh, I can do this. Energy is a scalar. Forces are here. Have you done field strength? Rayan will have.
Yeah.
So field strength has a direction.
Yeah.
It would be a vector. But the energy doesn't. You've done electric currents and electric fields last year, right?
Yeah.
So electric potential is here,
Yeah.
but electric field strength is a vector. That's why the adding up is very different.
Yeah.
Make sense? Okay, I'm going to leave it at those. What else do I have to do? Okay. How do I actually represent a vector? What we usually do, till we get to the algebra stuff, is a vector. Its magnitude is represented by the length of the arrow, and its direction is represented by the direction of the arrow. Here's another vector. Here's another vector. No, that wasn't a vector, it wasn't straight. Here's another vector. How do I know whether two vectors are equal? How do I decide whether two vectors are equal?
Like in force?
Is this one equal to this one?
No.
Because?
It's not the same.
It's not
Same what?
It's not the same shape. Oh, it's not the same size. Not the same length and not the same direction.
Okay, so are these two equal?
No.
Because?
Because one's slightly longer than the other.
Okay, assume they're the same.
Yes.
Notice though, I don't have to draw it exactly on top of here.
Yeah.
They are the same if they have the same magnitude and direction, regardless of starting point. Regardless of starting point. As long as they have the same magnitude and direction, they are equal to each other. I want to give them names beyond it's that arrow and that arrow and that arrow. The nice thing about standards is there are so many to choose from. There are a few. So I can go, if this is A and that point is B, then this vector is AB with an arrow. It's the vector that goes from A to B.
Why can't you just call the arrow the whole vector?
You can. You can call it little a with a squiggle,
Okay.
little b with a squiggle, little c with a squiggle. You can. But if you want to say the vector that goes from this point to that point, you can use this notation and it's not ambiguous. This is, everyone understands this is the vector from A to B. And we'll do a lot of algebra with all of this stuff. You'll notice also in the syllabus, there's a D here that's bold. You can't do bold when you write by hand, at least not very easily. So the convention is you put a squiggle on it. But in a printed document, you can assume that a bold little letter means a vector. Bold or a squiggle.
What's the hat for?
So if the magnitude of my vector, if this distance, I need a different colour for this, hold on. If this distance is exactly 1 unit, then this is a unit vector, and it gets a hat. So what I could do is go, I could then draw here this vector here is exactly 1 unit long in the direction of A, so it's A hat. It's a unit vector in the direction of A. That's what the hat does. We'll do a lot with unit vectors soon, but not just yet. So, vector equality, scalar multiple. Okay, scalar multiple. If that's A, what's 2A?
Twice as long.
In the same direction. What's, let's go, what's negative half A? Shh. Somebody else tell me?
Half the length from backwards.
In the opposite direction, correct. That's negative half A. So you just multiply by the scalar in front. That's why it's called scalar multiplication. Scalar multiple of a vector. How do I, resultant. How do I add and subtract? To add vectors. What am I going to do to add A and B?
Of the same direction?
No, this is A, and
Oh.
this is A, and this is B. How do I add them?
With
What's it going to mean to add my vectors?
With a triangle.
What kind of triangle?
A right angle triangle.
A right angle triangle?
Yeah.
Then I need to give you a different vector. What's A plus C look like?
Where's C? Probably still a triangle somewhere.
It is a triangle, it's not a right angle. Place the start.
Oh.
I'm going to give you a rule. Place the start of the second vector at the end of the first, then join start of first to end of second. Let me show you. So, if this was my A, and this was my B, then this is A plus B. Put the second one so it starts where the first one finishes, and then the vector from where you started to where you finished is your new vector, is your sum. Let's try A plus C. Have a go in your book. Draw yourself an A that looks about like this and a C that looks about like that, and then add them.
Does it matter which one's first?
Good question. Try it both ways and tell me. It's a very important question. You need to know the answer. I mean, you can use a ruler if you want to. If you want to get it precise, you should use a ruler.
Which one? A and C?
I want you to add A plus C. Okay, so what am I going to do? I'm going to get my C. I'm going to stick it on the end of my A. And then this is A plus C. What did you find, Ben? If I do it the other way, what happens?
Oh, I didn't actually do that.
Well, what happens if I get my C, and then I draw an A? My C's are not the same. Oh dear. My C's are not the same. Hold on. That's better. And then I draw an A. And my result here, hold on, that was A.
A and C.
And this is C plus A. And they should be the same. In fact, if I draw both of those pictures at once, let me get a black for that. If I draw both at once, C, A, I get a parallelogram. That one's not very precise because I haven't used a ruler and haven't got lines to help me line it up. You will end up with a parallelogram. This is sometimes called the parallelogram rule for adding vectors. Some people just call it the triangle rule. The syllabus says triangle rule.
Do we need to prove that?
No.
Okay.
What it does mean is vector addition is commutative. You can do it in either order. It's exactly the same result. You will remember matrix multiplication was not commutative.
Yeah.
But vector addition is commutative. Okay. So then what is A minus C? How am I going to do that?
Good question.
Well, this is really a scalar multiple, right?
Oh, negative C.
So what I'm going to do is get my A. That was too long. Get my A, and then I'm going to subtract the C, and that's negative C. So, I've lost track of what colours I'm using. So this vector here is A minus C. And just like numbers, if you go C minus A, you should get a vector in the opposite direction but the same length. No, you won't. Yes, you will. C minus A, maybe not, I've got to think there's three. C minus A is C plus negative A. So we're going to go C, it was meant to be a bit longer, I'm not good at this, plus negative A, I guess it will work. Good, I was worried for a minute. And I should get C minus A. Same vector, opposite direction, allowing for my inaccuracies because I don't have lines and rulers. Make sense?
So you get the opposite direction if you minus.
Well, it's exactly like numbers. This is the negative of that, right?
Yeah.
Exactly the same as numbers. Addition works how you think it will. The syllabus calls it the triangle rule, and the textbook calls it the parallelogram rule.